welcome back. I think we're ready to start session 7, Advancements in Database Technology and Analysis. We have a full session here, 5 speakers. First will be Kyle McKillop from USDA, who will give a presentation about food composition and graph database, USDA's FoodData Central Technology Transfer to a Neo4j graph database. Next, we'll hear from McGinty from Ohio University, who will present evolving chemical composition data representations of food using semantic web. Third will be Sidra Ahsan from NCI, who will present guiding principles and considerations in transfer and sharing of research data. Fourth will be Jaspreet Ahuja, also from USDA, presenting IngID, a framework for parsing and systemically reporting ingredients used in commercially packaged foods, its development, current features, and potential applications. And then Colin Kay will be our final speaker. Colin's from North Carolina State University and will present development of a nutrition knowledge database to support precision nutrition. So if we could get started.
Hi, thank you for joining us today. My name is Kyle McKillop. I'm the lead of USDA's Food Data Central, and today I'm going to be talking about USDA's Food Data Central and the integration of graph database technology. There are a few topics that I want to give background on before we get started today, so you have a good foundation of what I'll be talking about. I'm going to do a quick overview of Food Data Central, followed by some definitions. What is a structured database? What is an ontology? And then ultimately, what is a graph database? I'll then move on to talk about why we chose to move towards a graph database and what our implementation looks like, things that we learned. I'll give some examples of some queries on the graph database and what they look like, and talk about next steps and takeaways for transitioning a database system to a graph database. Now, we've seen a lot of presentations on USDA's Food Data Central at this data bank conference, but just in case you missed any of those prior presentations, I do want a quick rundown of what FDC Food Data Central is because it's important for the context of moving forward. So Food Data Central is an integrated research-focused data system that provides expanded data on nutrients and other food components. It is a publicly accessible website at fdc.nal.usda.gov, and I invite anyone who hasn't been there yet to go check it out. And on Food Data Central, we have 5 distinct data types. There's Foundation Foods, released in April of 2019 with the launch of Food Data Central. Foundation Foods is data for food components, including nutrients, derived from analyses, and it includes metadata for a range of single food and ingredients, providing potential insights into component variability. Experimental Foods, which is data produced under experimental conditions, such as derived from an experimental design or potentially about new analytical methodology, and aren't necessarily to be used for reference. We have SR Legacy Foods, a historic data set that had its last release in April of 2018, but still includes valuable data on food component, including nutrients that are derived from analyses, calculations, and published literature. We have Survey Foods, also known as USDA's Food and Nutrient Database for Dietary Studies, that includes 65 key food components, including nutrients, and weights for foods and beverages as reported in the What We Eat in America Dietary Survey, which is a component of the National Health and Nutrition Examination Survey, or NHANES. And last but not least, we have Branded Foods, which is label data provided from data manufacturers, both in the US and internationally, for branded food label data that's provided in part because of a public-private partnership, of which you might have seen the presentation for. And to give a definition of graph database, I actually want to start with what people are probably more familiar with, which is a structured database. So when we launched Food Data Central in April of 2019, it started with a traditional SQL database system. It's a structured database. So a structured database is anything that's considered tabular format. And you are probably familiar with this if you've used desktop applications such as Excel and Access. And even if you're some form of database administrator, you probably have experience with database applications such as MySQL, MS SQL, or Oracle. So when we launched FoodData Central in 2019 with a structured database, we were always considering what it was going to take to future prepare FoodData Central. We had some considerations such as artificial intelligence and machine learning, where that technology was headed and what we needed to do to make sure we could best interface with that technology. We had an understanding that food composition is really a part of a larger system. That is, what are the agricultural practices that are impacting food composition, and what's food composition's impact on human health? And lastly was the want and need of integrating an ontology. And for that, let me define ontology. And I think this image on the right best explains what an ontology is. This is a visual representation of the FoodOn ontology. You can get to it to the link provided. But an ontology codifies knowledge in a way that it standardizes terms, standardizes definitions, and relationships between those terms and definitions, and makes it machine operable so that you can take advantage of things like artificial intelligence and machine learning. You can see the example on the right shows you the relationship between a caramel apple and an apple. An apple is part of a caramel apple that is derived from the apple tree that you can find an identifier for, a taxonomical identifier for, in the ChEBI taxonomy database. And so using this codified knowledge, you can see that our next step is to consider how to take advantage of this, which brings me to my definition of graph databases. And to the definition of graph database. Graph database is a paradigm shift in storage and retrieval of data. On the left, I've given an example of what a tabular format for our data looks like. We have a table for food, a table for components, and a table that joins the two called food components. In food, we have an identifier for our Honeycrisp apple. In components, we have an identifier for our total sugars in grams. And in the joining table, food components, you can see by joining the two IDs, we end up with a value 12.2. On the right, this is much easier to decipher without having prior knowledge of how food and food components are related within our data set. I have two nodes. One is the Honeycrisp apple and one is total sugar. And I have a value between them, which is an edge called has component. And if you follow that line, you can see apple's Honeycrisp has component total sugar with a value of 12.2 and a unit of measure in grams. And you can hopefully visualize what this sort of paradigm shift looks like on a physical level in the database structure. So maybe now you understand the differences between a structured database and a graph database, but why would you want to move to a graph database? First is that physical integration of ontology. You might have noticed that the graph node and edge structure looks exactly like an ontology is. And so having a physical integration from our data layer to that ontology means we can take advantage of that node to edge structure. Second is the flexibility of adding new nodes and edges in the graph database. Adding tables and adding columns into a structured format can be extremely expensive, whether that's time, whether that's memory in your computer, or whether that's just having a contractor go in and modify your database structure and then modify your views to make sure that that data appears in your application or appears in the reports that you're making. In a graph database, adding new nodes and edges and defining these are as simple as going into the data structure and doing as such. Not requiring the contractor, it's not expensive, and sort of going in and doing this adds a lot of flexibility for how you want to proceed, especially if you don't know the definitions of some of the terms that you might be using. When it comes to our database and having a flexible format, we have a lot of metadata, and these metadata have very different definitions to these terms that we're putting on. And this allows us the flexibility of not knowing what metadata we're going to be collecting in the future. And the last is the traversal of the graph. And so everyone's familiar with Google Maps, and I put the picture here as an example of finding the shortest distance between point A and point B. But there are other pathways between point A and point B. And so by using artificial intelligence and visualization tools, we might be able to insight data and insight pathways on our data that we haven't seen before. In the case of Google Maps, it tells you, hey, you can take an alternate route, but it'll be slower. Or you can take this way. It might be faster, but you'll incur a toll. So what does that look like when we do and traverse through food component data, and what can we potentially learn by finding links between data in our system? Now, this isn't all said and good. There's things you need to consider when moving towards graph, and probably the two biggest points are, while you have more powerful querying of your data and asking interesting questions, the more complicated the question, the more slower your search results will come back. The other aspect of this is making sure you sort of have the expertise that you need in Graph Database. Graph Database uses what is called a cipher language for searching through the database. And there's training on this, but to fully understand how to take advantage of this requires some formal training and background. So now I'd like to talk about what we did to implement Graph and the steps we took to make sure we were moving towards the right path. So our first phase was a proof of concept phase that we started right at about the launch, right before and past the first year of our launch of FoodData Central in 2018 and 2019. Our proof of concept was taking a limited data set of what was in FDC and trying to link it with some ontology terms and relationships, with the goal of transitioning from a SQL to a graph database with the output of the search functioning the same way as it did during the structured database, and seeing that if we could integrate ontological terms into the search results and display them. And the outcome was successful. We successfully got the search to work the same way that was using for the structured format, and we were successful in integrating ontology terms. You would search for a bean and it would be able to sort of explode and say, more specifically, are you interested in a specific variety of bean? Here's its definition and here's its nutrient information. And reviewing the search from the structured database and reviewing the search on the graph database, there was a very minimal impact on retrieval speed, at least in the proof of concept. And you'll see where that got us as we sort of scaled up moving forward. The second phase was determining that we were choosing the right technology. So we proved that a graph database would work, and for that first phase, we used a graph database called Neo4j. But we wanted to make sure that the technology we were using was most appropriate for where we were going. And this research was originally conducted in late 2019 and early 2020. So we used Neo4j, and after doing a cost-benefit analysis and looking at alternatives, we decided to stay with Neo4j. Neo4j has the maturity. They were the inventors of this particular type of graph database and have existed with a maturity that doesn't necessarily exist in other graph database technologies, which means with the maturity comes an existing support network. You have a lot of examples online of people trying complicated things, trying to search through and insight complicated things with their data. And that existing support network is very important for making sure that you're going to have the stability and support needed as you expand yourself. And it also had open source licensing. So we're using the community edition for FDC, which is an entirely free licensing that we can use to put out our database. And has worked for us in publishing at a cost that is free and that we can maintain moving forward. We had some hesitancy in choosing Neo4j in early 2020, and it was primarily because of the format of the graph database meant that it had weaker support of ontology integration. And I have an asterisk here because I believe that things have changed since we originally did this cost-benefit analysis. And Neo4j has, with the sort of explosion of ontology expertise, have done more to work towards making sure people can integrate ontologies from technical standards and formats, and make sure that Neo4j sort of is able to support these this ontology integration. And the main reason for choosing Neo4j and the largest upside for us was scalability. Because we were a public-facing website that people needed to be able to access with, for example, 3 million API calls a month, we needed to make sure that we were able to scale up our application and still be a public resource where people could get to our application and pull our data. And then finally, we transitioned into a graph database. In October of 2020, FoodData Central was launched with a graph database background. There was no sort of hubbub that we had done this. Instead, our goal was to make sure there was little to no impact on application users, that there was little to no impact on API users, and that the API features that existed, that they needed to stay intact and continue to function as they had prior. So we wanted to show that the transition to graph was not detrimenting the website and was able for us to continue launching and using FoodData Central as people were using in the past. And with that, we were primarily a success with some pitfalls that I'll talk about soon. But I'm glad to say that since October 2020, we've been running off of Neo4j, optimizing the platform, and have been able to use it as a full platform. But again, not without some issue. I would say that the key learning we had when we transitioned into scaling it up to the full application was there was a noticeable slowdown in record retrieval and search. So while this was very minimal in our proof of concept, once we expanded it to the entire data set, we went from hundreds of records to millions of records, that sort of time increase from part of a second grew to a couple seconds. And a couple seconds doesn't sound like a lot, but when people are using your website every day, a couple of seconds can get annoying. We have resolved that since with some temporary fixes. But when we sort of looked into why this was scaling up, Neo4j advertises that this shouldn't happen. So we looked at what was happening with our graph and we realized that it needed optimization. When we transitioned from graph from the structured database, we inherited structured database types of design patterns, which means that we had some redundant and unnecessary nodes that existed. We had that node and edge system, but we were storing all of our data on nodes and none of that data on edges. You might remember I gave an example where the data was stored on the edge with the value and unit of measure for total sugar. And so we needed to sort of take back, look at the graph that we had transitioned and realize that it needed to be, I wouldn't say redesigned, but maybe restructured to take advantage of having a node to edge format. And so with that, we've been doing that, and that will be a part of an upcoming slide. But I think this is a good moment to stop and talk about takeaways from us transitioning and things you should consider if you want to do this. The first is why and when to use a graph database. And the reality and the question you should be asking yourself is, do you want some of those affordances? Because if it's just a matter of reporting on data and collecting data, maybe not. Maybe a structured database is the way you should stay, especially if that's where your expertise is and historically what you've done. For us, moving forward with artificial intelligence, moving forward with ontology, we do think graph is the right direction, and we're going to continue down this path. The second to consider is if you are transitioning, you should consider building your graph from the ground up, making sure you're taking advantage of this paradigm shift. What you've done in the structured database isn't necessarily accurate for a graph database. And to do this, you really need some expertise. You need someone who has experience with graph and or ontology, which has similar sort of node to edge structure, to make sure that you're designing in such a way that you're taking advantage of the graph structure. And that's where we are today. So we're moving toward a better graph design as we sort of clean and optimize our database over the last couple of years. And we're getting into this discovery process on our data. So I thought I'd spend my last few minutes showing you some examples of what our graph looks like today and some of the queries that we do. I'm not going to define the Cypher query language today, the language used to query the Neo4j data system. But here's an example of us querying iron and beans. And I've highlighted in red the identifier for iron and then our search term for beans. And look at this beautiful representation of iron and beans within our data set. The colorization of Neo4j, this is built in and a part of their system. You can see the iron representation in gray. You can see our samples in red, and in pink you can see our foundation food and how all of these values might represent and be compared against one another. And what's great is that query can be used to export to a tabular format, so something that you might be more familiar in reporting. So it's hard to report on that graph structure, but you can look at this data and start to consider what it means through Excel and bringing it into other platforms. One more example, this is a query on discovering sodium changes in branded food products. And the graphical representation with sodium in the middle as the gray node, products in the blue nodes, and iterations of each one of those products in the yellowish orange. And again, easily exportable to a tabular format that you might be pulling in or reporting on for other needs or pulling into other applications. One thing to mention, if you're interested in Neo4j, they provide a lot of different resources for you to learn about how to use Neo4j and a lot of resources on searching and training that's freely available currently on their website. And with that, I think our next steps I've already made clear. We need to finish that optimization of the graph database. I think we're nearly there. We're doing a couple more projects to finalize that. Continue our integration of ontology that we hope to have in our next major release, or at least in some form that people can view how we've integrated ontology or how to integrate ontology. And updates to our interface to start to take advantage of graph database and our ontology development so that it impacts you as our users for searching and retrieving data in our system. And with that, I'm ready to take questions. You can contact me at the email address here. You can also fill out the form at FoodData Central at the link provided here if you have questions about this particular project or anything about FoodData Central. Thank you.
Hello, I'm Hande McGinty, and I'm a research associate professor at Ohio University. I'm collaborating with the USDA's FDC team, and today I'll talk briefly about how we have been approaching the mapping and encoding of chemical composition components of food products using Semantic Web. I'll start with examples of how we see representations of chemical composition components in food currently on different sites and databases. I'll follow that with why I think there is interest in better representations of chemical composition components in food products. My talk will continue with giving some approaches that we're currently using and evolving for representing the chemical composition components and how we model a food product and where we put chemical composition component in our model. I will highlight some of the challenges we're facing and we've faced so far, and we'll talk a little bit about how we have been approaching the problems we tackled. When we look at food and agriculture data and data sources right now, we see that there are many different data sources kept in silos, often separated from one another, sometimes without any mapping or connection. One of the biggest data sources in the USDA's FoodData Central, FDC, with its 35 plus years of experience in representing data regarding food products and their chemical composition components. Almost all food data related portals use the USDA data sets for either representing their data or mapping their data to this resource. Of course, there are other data sources that are freely available. For example, research data sets from universities and institutes, UN's Food and Agriculture Organization's data sets, and other databases within the USDA, or other government agencies such as the FDA, EPA, NIH, and others. In addition to these free and research-focused data sets, we see many proprietary data sets that are available for consumers as well as the food and agriculture industry. There's growing interest in other data sources that connect to this set of food-centric data sources. For example, the recent pandemic heightened our interest in sustainability and environmental data surrounding food, as well as the supply chain data that is related to it. Of course, public health, diet, and nutrition have always been a crucial interest when we talk about food products from consumers, researchers, and of course, government agencies' point of view. So when we see these data sources all separated, but holding related data that's valuable for further analysis, we really would want to look at some of the core commonalities in the data sets. And chemical composition components definitely fit the bill in that sense. So I'll try to point out some challenges here, but we have very limited time, so I won't be able to go through every single resource. I'll try to highlight the current challenges using examples from particular sites. For this presentation, I'll give you examples from the FTC side and FooDB, because FTC is one of the most cited resources, and FooDB is one of the resources that has the most number of mappings and connections. However, I hope that you won't get held up on these sites themselves, but take away the message that on every single side of one of these sites, you'll see different representations and different sets of chemical composition components for the same foods. So I would like us to take a look at bananas as an example food product. You see a partial screenshot showing bananas on FTC's website. And you can see the nutrient components are presented on this web page. And as I mentioned before, FTC has over 35 years of data and experience that it provides for its users. It has 4 main data sets, and the component results are either calculated or using different methods or measured using analytical chemistry methods. So when I search the same product on other data sets, and like I said, I decided to pick FooDB for this presentation, you can see that there are differences in representing this data. On FooDB, when we search for bananas, we get the human description of banana and its chemical composition components. As I said, I picked FooDB because it's one of the resources that aims to map data to as many resources as it can. So as you can see, there are many external links for potassium here, which is one of the chemical composition components of banana. However, for banana, when you look at chemical composition components on FooDB, you see over 4,000 chemical composition components. And when we see that many components, as a user and a researcher, the question quickly becomes, which one of these 4,000 components, for over 4,000 components, are the most important or relevant to me or my research? As you see, on this partial screenshot, some of these component data comes from the USDA's data sets. And USDA keeps track of how all the data is generated and represented on the FTC's webpage. However, when we talk about 4,000 components, we really start worrying about how all of the rest of the data are created and what methods have been used to find these components that are represented on the site or any other site. When we start digging deeper and start looking one component at a time, for example, let's look at glucose in FTC and FooDB, you will see that the representation is slightly different. For example, when we look at Canadian nutrient component representations for sugars, and apart from what we see here, we don't see total NLEA because they're using different methods. But on FooDB, one of the mappings, as we talked, that it has a lot of mappings. One of them is to ChEBI, which is a chemical ontology implemented and maintained at the EBI, European Bioinformatics Institute. So as you can see, the glucose they're referring to that's mapped on FooDB, it has a role fundamental metabolite. Similarly, when we look at this PubChem reference on FooDB, for the sugar, for the glucose and banana, is annotated as a corn sugar on PubChem. So again, when we look at these informations and these parts of references, it gets slightly confusing to the untrained eye and the unfamiliar users, and definitely confusing for the average customer. So at FTC, we focus slightly more than 430 chemical composition components, and we recently went through a mapping exercise as a part of the ontology that we're building. And when we try to map the components at the FTC, our experts suggested a different PubChem ID for the glucose and bananas. As you can see, the PubChem ID mapped on FooDB and PubChem ID suggested by their R domain experts are different. Again, I'm not trying to say that one is better than the other or you should prefer one over the other. I'm just trying to point out the differences, which leads to ambiguity and might possibly lead down to different analysis downstream when you try to analyze this using different data sources. So I think we clearly established that for the average user and untrained eye, all of this is ambiguous and confusing. And when we look at who else needs better representations of chemical composition components in food products, we would see that local and global food and ag organizations, United Nations and FAO, hospitals, the NIH, American Heart Association, and of course, researchers who has a broad range of interests for research and development of new methods. When we look at local and global organizations, we do see interests regarding sustainability, crop details, irrigation, and other supply chain related details. Similarly, when we look at health organizations, their interests are more human and animal centric. For example, recently the NIH emphasized a new research program that looks at holistic human health that takes the environment and biological factors into consideration, which obviously includes food and agriculture data. Similarly, a long list of different interests in the research community, from smart food checks to periodic table of foods to the different standardized vocabulary being built around the food and agriculture data. So our approach also builds on standardized vocabulary and semantic web. We are using a systematic approach in modeling our food product data, using the ontologies and axiomizing the chemical composition components of food product. Before we move on to that, I want to briefly give a definition of what an ontology is. An ontology defines a set of concepts and relationships in a subject area that we want to model mathematically. In the ontologies, we see concepts, properties, and the relationships among different concepts. when we're building ontologies, we usually look at complex subsets of different disciplines. However, it is important to keep in mind that ontologies usually aim to limit complexity. In the ontology realm, we usually talk about concepts and relationships, and there is a huge philosophical discussion about what we can call a concept and what we can't. During this talk, I'm not going to get into depths of that, and I will call everything that you see as a node on any graph as a concept, and the edges between those nodes as relationships. We can define concepts like sets and the object relationships as the concepts like mathematical relations. As you know, in mathematics, there are many different ways to define sets and name the sets and the relations. So similarly, you can name your concepts and object relationships in the vocabularies as you see fit. At the expense of sounding overly simplistic, I will say that everything that has a chemical structure, and that is all matter, is connected. Then the problem becomes, which one of the many connections among different concepts or disciplines do we need to answer for our questions? What other pieces of information are required, and what is optional? Keeping those questions in mind, and with the data we have in our data sets at FTC, we came up with a draft model for a food product that is in our data set. We are following a systematic way, a methodology that keeps domain expert involved in deciding on the concepts and relationships we should include in our model. We follow a modular architecture with a database backend to generate our ontology in a semi-automated way using our methodology that's been established and used in nationwide NIH projects previously. This methodology, we allow a continuously evolving ontology that grows systematically in modules as we get more data and connected more or different data sets, and as we develop different interests. In my talk today, we will focus only this small portion of this model, and nutrient components is a subclass of chemical composition components in the food product. As I mentioned previously, one of the exercises we went through at FTC was to classify 430 plus nutrients as we are focusing on, and those condensed set of nutrient components, and we did add that to our ontology. We followed our task by adding cross-references of these composition components to PubChem. But as I mentioned, we did face some challenges when we were going through this exercise. We've noticed that there is a fast-paced data creation, and because of that, there has been new information that hasn't been referenced in prior data sets, or data sets such as IngID codes that didn't even exist a couple of decades ago. That then leads to what I would call in computer science incomplete documentation and initial reference during the creation of this data. Another challenge that we've faced as we looked at other data sources online, we've seen that there is automated term matching, and that's not always an exact term matching, but sometimes represented as such. We have seen resources that has mappings, but really missing the justification as to why that mapping is represented on that particular side and how they came up with that mapping. We are definitely lacking in computer science methods and tools, which I would call collectively as resources for component mappings, which leads to then inconsistent mapping practices on different platforms. One mapping that's available or justified in one site is not available on another site. Incomplete chemical composition profiles are available on different sites. Sometimes it's because they focus on a set of nutrient components, and other times it's because that data is not available for scraping or production. But then again, that then causes for inconsistent representations of chemical compositions of foods on different platforms. What we have been using as our approach to remedy some of these challenges is evolving and building onto the ontologies that fit the needs. We are really putting our efforts for better documentation and initial reference creation as we create our data. We're aiming for exact matching for a select number of nutrient components and annotating resources mapped using ontology mapping practices. We're consistent in our representations of chemical composition components of foods using our food product model as a basis. And we take advantage of the domain experts that are working with us and use their reviews for these mappings. Of course, the aim is connecting using FTC's ontology and enabling knowledge graph generation for other pieces of data. And to do that, we really need to focus on how we can represent chemical composition components better. And it's a question that we are still tackling today as we're building the ontology using our food product model. I would like to acknowledge the team that I'm working with. It's always a team effort, as you know. And I thank everyone very much. And I'll take questions now if you have.
Hello everyone, my name is Sidra Ahsan and I am a Senior Technology Transfer Manager at NCI, National Cancer Institute of the National Institutes of Health. The title of my talk today is Guiding Principles and Considerations in Transfer and Sharing of Research Data. Many of you are involved in sharing and receiving research data to help answer big and complex scientific questions. In this talk, I will focus on some important guidelines that apply to sharing research data, which are typically memorialized in data sharing agreements. I hope that by the end of this presentation, you will have a better understanding of the general principles that apply to sharing data between institutions and how data sharing agreements can enable and facilitate better scientific collaborations. First and foremost, why use an agreement when sharing research data? Agreements protect your proprietary data. They allow for protection of non-public data or information, such as information that has not been published, that has not been presented. Also, agreements allow for sharing of data in an ethical and secure manner. They reduce the risk of a bar against patenting. For example, if you have any data that may be included in a patent application to support your invention, you probably want to protect that. Agreements also protect the rights of all parties, the party that is providing the data and the party that is receiving the data. Most importantly, agreements help avoid any future disagreements between collaborating parties. Typically, data is shared through some form of a data transfer agreement that I will call DTA from now on. A DTA is a contractual agreement that is used to define how exchanged data may be accessed and or used. It establishes the terms and conditions under which the data provider will provide and the data recipient will receive and use the data covered under the agreement. These types of agreements may have different labels, such as data use agreement, data share agreement, data transfer and use agreements, but the premise remains the same. There are several types of data that you can share under a DTA. General research results, such as results you produce in a lab, that may be shared. Data derived from human subjects, such as data coming from a clinical study, a diet and exercise study. This human subjects data may be de-identified, coded, or identifiable. Different institutions have slightly different ways of defining what constitutes de-identified or identifiable data, and there are also some specific regulations that apply to those, but I will go into further detail later in the presentation. It is also important to note that data transfer agreement is used when the recipient will use the shared data for research purposes. It is distinct from confidential disclosure agreements and non-disclosure agreements, because CDAs and NDAs are typically not used for research purposes. They are used for discussion or due diligence purposes around confidential information, that is information that has not yet been disclosed. But DTAs are specifically used for sharing data for research purposes. Now, what are some of the considerations for sharing data that you want to keep in mind when you are ready to share data with someone? First and foremost, can you share the data? Do you have the rights to share it? How did you get the data? From patient records? From a project where you collected it directly? From a different institution? Maybe you received it from a collaborator. All of this ties into the question of who owns the data. And my next slide will further discuss that. If you did receive the data from another entity, you want to make sure that this entity that provided the data to you, most likely under an agreement, allows you to further share their data with others. Next big question is this data derived from human subjects? If it is, then was it collected with consent and authorization? Is it covered under any regulations such as HIPAA, Privacy Act, or GDPR? Is there any IRB review required? In most cases, for any human subject data, whether it is de-identified or identifiable that is being used for research, an IRB or an equivalent reviewing body's approval is required. After you have considered all of this, then you want to figure out the correct agreement to share your data. You can use DTAs or DUAs. There are also some model templates that certain institutions have agreed to use, which ease the burden of negotiating agreements. One of those is the Federal Demonstration Partnership, DTUA, that NIH uses. Also, data sharing provisions may be incorporated in other agreements. Let's say you're interested in sharing some patient samples with your collaborator through an MTA, a material transfer agreement. You also plan to share data associated with these samples with your collaborator. You don't need two agreements. The data sharing provisions can be incorporated into the one MTA that will allow you to share both materials and data. Lastly, you want to make sure that all proper terms are included in the agreement based on the type of data you're sharing. A DTA for sharing human data will have distinct terms specific to protection of human data as compared to a DTA in which you are sharing general lab research results. As I mentioned, one of the first considerations when you are ready to share data is that can you actually share the data, and if you have the right to share this data, and that ties into ownership. So one of the most important considerations in data sharing is ownership. So who owns the data that you want to share or gain access to? Typically, data is owned by the institution that produces it. So any data that is produced by an employee at NCI during the conduct of his work at NCI is owned by NCI. Typically, data which is produced under grants and contracts that are funded by NCI are also owned by the institutions that produce it. However, NCI may have rights in the data that is produced which are specified in the funding agreement, but the ownership stays with the producing party. There may be some exceptions to this ownership where there is already a pre-established agreement between the parties, where one party has already stated that they want to own the data that the other party is producing. This is typically not the case with government and may happen more in the private sector. The next very important consideration is intellectual property that may apply to the data. So the first one is copyright. Copyright is a type of IP that protects original works of authorship. Copyright does not apply to data because data are considered facts under US law. They are discovered, not created as original works. Thus, data as a collection of facts is not protected by copyright. Second one is trade secrets. Trade secrets are a type of IP that include, amongst others, compilations of information that have inherent economic value. Because they're not generally known, they're not readily ascertainable by others, and the owner takes reasonable measures to keep them secret. Data may be protected through trade secret. For this, the data must have commercial value, be secret, and be subject to reasonable measures ensuring data's secrecy. Last but not the least are patents. Patents only apply to inventions, not data. These inventions can be processes, machines, manufacture compositions of matter, improvement, design, etc., but not data. Data may be used in the patent application to support an invention. However, it's not the invention itself. Patents may apply to data only if the data collection leads to a new and useful invention. For example, a US patent has been awarded in respect of how a compilation of data was physically stored, since the way it was stored was novel and it allowed the stored data to be accessed much quicker. Now I want to discuss some of the important regulations that apply to sharing of human subjects data that may be included in a DTA. These regulations are fairly complicated and require an hour-long discussion on their own. But for the purposes of this presentation, I will provide a brief overview of some of these regulations that apply to human data that may come up in an agreement. First one is the common rule, which covers research of all human subjects and identifiable information alone, or it may be supplemented with other regulations, such as HIPAA. It basically applies to how you collect data, but it may also apply if you're collecting HIPAA data. Let's say you're conducting a survey of how many people in a given population have a gluten allergy. If the people in this given population you're studying are just sharing information about their gluten allergy, a condition they may have, and you are not a medical provider, and you will not be using it for any medical treatment, it's not technically HIPAA data. However, common rule may apply here. Next is the HIPAA privacy rule. The HIPAA privacy rule establishes conditions under which protected health information may be used or disclosed by a covered entity for research purposes. These covered entities in HIPAA are health plans, healthcare clearinghouses, or healthcare providers who transmit health information in electronic form. Research institutions may or may not be covered under the HIPAA privacy rule. For example, NIH is not a HIPAA covered entity. Privacy Act. Privacy Act protects records about individuals retrieved by personal identifiers such as a name, social security number, or any other identifying number or symbol. It also prohibits disclosure of such records without the prior written consent of the individuals to whom the records pertain. The most important part to know about the Privacy Act is that it binds only federal agencies and covers only records under the control of federal agencies. Hence, NIH complies with the Privacy Act. Another notable regulation is the General Data Protection Regulation, GDPR, which seems to be the most exciting one for everyone nowadays. GDPR is applicable to data collected or processed in the EU and other economic EU area or data accessed from EU. So let's say, for example, a postdoc from Italy comes to the US and is working at an NIH lab in Bethesda, Maryland. The data she produces at NIH in the US is not regulated by GDPR. If the same postdoc goes back to Italy and gets a job at University of Milan, and now she wants to access this NIH data she worked on in the US, her access, because now it's from Italy, will be regulated by GDPR. It is also important to know that GDPR has its distinct standards and definition, and that there are notable differences between GDPR and HIPAA. Some of the differences are that the standards of de-identification are not the same, definition of anonymized is different, there are some markedly different standards between GDPR and other laws that commonly apply in the US. Now I want to talk about what goes into a DTA. Here I have listed some of the typical components of a DTA. First, a DTA should identify the parties to the agreement, as in who is providing the data and who is receiving it, and there may be multiple providers and receiving parties. Then the origin of data, as in where did the data come from? Is it from a study that the data providing party conducted, or did they receive it from a different party? Then it may also contain limitations on use of data. It is important to control the use of the data that you provide because there may be some related IP, so you want to make sure that the party receiving the data will only use it for the research project they requested the data for and not any other ongoing projects they may have. Next, a DTA typically limits further distribution, which means the receiving party cannot share the data you provide with anyone. You can include language in there allowing them to further share the data with collaborators, contractors, or any other agents that are working on the research project, but that should be explicitly stated. You also want the receiving party to acknowledge the source of data and public disclosure, such as presentations, abstract, or manuscripts, so the party that produced the data gets its due credit. There is typically additional legal liabilities and obligations language in a DTA, which also includes some of the regulations that I mentioned before. And then there may be some language related to confidentiality obligations that is only present if the data or any information being provided in the DTA is confidential. And if these obligations are mentioned, typically what institutes confidential information is also defined in the agreement, and there's also a term. The point of this is to basically tell you that all of these components are there for one major reason, and that is to protect the rights of all the parties that are involved. The party that is producing the data, the party that is sharing the data, and the party that is receiving the data. This is an example case study of a DTA that was recently established between NCI and two other institutions. So NCI investigators were interested in obtaining de-identified human subject data from the multi-ethnic cohort MEC study to investigate the association of dietary seaweed consumption as a modifier of risk of breast, colorectal, and prostate cancers. In order to obtain the data from the MEC study, NCI investigators had to meet two requirements. Submit a project application that describes how they plan to use the data, and establish a data transfer agreement that outlines obligations of all the involved parties. NCI investigators submitted the project application to the MEC Study Reviewing Committee and contacted their tech transfer office to establish a data transfer agreement. This is a very typical process. Upon approval of the project application, a DTA was negotiated and executed between the MEC Study institutions that produced and owned the data and NCI. This DTA allowed NCI investigators to receive the specified data and conduct their proposed study. I am using this DTA as an example because it contained fairly standard terms that I went over earlier in the presentation. Some of those terms are listed here, the most important ones. So first of all, the DTA identified the parties to the agreement, which were NCI, and the two institutions from MEC study that actually owned the data that NCI needed. The DTA also established permitted uses, which meant that NCI could only use the data to conduct its study where it is investigating the association between seaweed consumption and risk of different types of cancers. The DTA also identified who may or receive this information. Typically, it would just be NCI, but NCI needed to share the data with some of its contractors who will analyze the data. So we put in explicit language that NCI will share the data with these contractors. So it was permitted in the agreement. The agreement also contained requirement to use appropriate safeguards to prevent an unauthorized user disclosure that is not contemplated by the agreement. It also contained prohibition on identifying the information or contacting any individual subjects. This is fairly common in a human subjects DTA, which this one was. It also required IRB approval or equivalent from the receiving institution. So at NCI, we were able to receive an equivalent IRB approval. And the DTA also contained language on how to dispose of the data when the research project is completed or the agreement is terminated. And so these were all of the obligations that NCI agreed to when it agreed to in order for NCI to receive the data from the MEC study institutions. In the end, I hope this brief presentation has provided you with some information that you were not previously aware of. Also, that it has helped you understand the process of data sharing and what goes into it. And you can use DTAs and how you can use DTAs to further collaborate and do amazing science. My name is Sidra Ahsan. Thank you for letting me present on this very important topic. And with this, I will take any questions.
Hello, my name is Jaspreet Ahuja, and I am going to talk to you today about IngID. It's a framework for parsing and systematically reporting ingredients used in commercially packaged foods. We'll talk briefly about its development, the current features, and potential applications. This is the outline of my presentation. Why are ingredients in packaged foods important to study? IngID, briefly about the methodology and complexities, followed by some examples of applications, and then we'd like to discuss some future possibilities and collaboration. Processed foods are quite a bit in the news, some with sensational headings, some funny, but more and more in scientific publications such as this from the American Heart Association. Why do we need a system to study ingredients used in packaged foods? Because they are an important part of the US diet. They provide over 50% of the total energy in the US, as per NHANES data, and are important contributors for several nutrients too. Reducing their consumption is part of the dietary guidance from the American Heart Association, and is also a proposed question for 2025 dietary guidelines for Americans. Food composition databases and food consumption surveys have generally focused on nutrients and have limited brand name information. Different brands of similar foods can have very different ingredients and nutrient profiles. Emerging research shows the need to look beyond nutrients. Other physical and chemical properties, such as the form of ingredients used, the matrix, additives used single or in combination, and bioactive composition may be important. There is very limited information on type of ingredients used in packaged foods and their consumption in the US. As per FDA guidelines, ingredient statements in packaged foods list all ingredients in descending order by weight. USDA's Global Branded Food Products Database, or BFPD, now has made publicly available ingredient lists for over 350,000 packaged foods. The ingredient lists are however present as a text block. So IngID was developed to enable parsing of this text block into individual ingredients and its systematic reporting. A prototype based on baked product categories was developed and tested, and now it has been expanded to several categories such as beverages, yogurt, candy, etc. This schematic provides an overview of the steps in the development of IngID. First, we identified top food categories, those that contributed over 1% of total sales. We used the IRI point of sales data for this purpose, and then we identified top foods among these categories. Second, we obtained ingredient statements for top selling foods. We mainly use the branded foods product database for this purpose. Then we parsed these ingredient statements into individual ingredients. We developed a custom program in R for this purpose. Then we found that there were several synonyms for these ingredients, so we developed a thesaurus for systematic reporting of these ingredients. And then we grouped these ingredients based on the research questions such as refined flour or wheat flour and so forth. As per FDA guidelines, ingredient statements list usual or common names in descending order by weight. Sounds simple enough, but we found that was not the case. Initial review of the parsed ingredients revealed that the ingredient lists are complex, inconsistent, and full of errors. And we needed extensive pre-processing before parsing for the parsed ingredients to be meaningful. I will show you a few examples of these issues that we saw. For example, here in the first one, the statement has an allergy statement too. So if left as is, these will get parsed as ingredients. So they had to be removed. Then we found random phrases such as made with smiles in the ingredient statement. And then several of 2% or less statements. Just in baked products, we found 50 different versions of this. While comma is the usual separator between the ingredients, we also found other words such as and is used. In the last example, we converted the and to comma to separate the ingredients. We cannot do so in this case of glucose and fructose syrup because that is one ingredient and is another term for high fructose corn syrup. And similarly, for mono and diglycerides or fatty acids, we cannot separate them out as two separate ingredients. The same case was with the term with. It can be used as a separator, such as in palm oil with soy lecithin, or it can be part of an ingredient name, such as in cocoa processed with alkali. So we had to create a file of these conversions or replacements. Then we found several cases. When I say several, I mean hundreds of cases in which the comma is missing, which would result in this getting parsed as one ingredient. We found that ingredient can be listed in various ways. As a result, we had to build a thesaurus, of which I will talk in more detail in my next slide. This just shows you a screenshot of the thesaurus for the ingredient wheat flour with added malted barley flour enriched. There are about 300 different ways in which this term is listed. And I did mention about the FDA regulation, which says the usual or common name, but we found that is not always the case. Some details of the thesaurus. We assigned preferred descriptors to equivalent ingredients. The variants can range from 1 for peach puree to about 900 or more for different types of enriched flour. The current thesaurus has about 16,000 items based on baked products, beverages, selected mixed dishes, and dairy products. We use several resources to guide us. And we are now looking at trying to automate this process of assigning preferred descriptors. For the next few slides, I will be focusing on baked products, which is what we use to build our prototype. The 4 categories we used were breads, crackers, cookies, pastries, and donuts. We obtained ingredient statements for about 6,500 baked products with BFPD as the main source, ensuring that we are representing about 66 to 90% of the volume sold. Then we parsed these ingredient statements, which resulted in about 7,000 uniquely described ingredients, but many of them were equivalent, so we assigned them a preferred descriptor, and these 7,000 uniquely described ingredients are represented by 1,460 PDs. They can be further broadly grouped, such as refined cereal grains or sweeteners, emulsifiers, etc. The sampling diagram here visualizes the most frequently used ingredients, and they are sodium chloride, sucrose, wheat flour, the fortificant nutrients such as riboflavin, folic acid, niacin, etc., soy lecithin, and flavors. And the most frequent group of ingredients are added vitamins, added minerals, refined cereals, non-hydrogenated oils, sugar, and salt. Overall, we can say baked products are composed mainly of additives, grains, especially refined grains, sweets, spice and flavorings, and oils. Slide shows the most co-occurring ingredients in top-selling baked products, visualized as a heat map. The darker color indicates co-occurrence of the pair of ingredients. Not unexpectedly, the highest co-occurrences are seen among wheat flour and fortificants such as niacin, folic acid, riboflavin, and so forth, and among these fortificant nutrients, and also with wheat flour with sodium chloride and sucrose. This small group of ingredients occur and co-occur very frequently in packaged baked products and form the core of the ingredient network. We are only presenting top occurring ingredients here, but this analysis can be used to determine the co-occurrence of any pair of ingredients of interest. For example, FDNC colors yellow number 5 and 6 co-occur 254 times in cookies, and this is possible with the use of the ingredient ID system. Additive type ingredients, which are defined here, account for 63% of all ingredients listed. Salt, sugar, fortificant nutrients, soy lecithin, and added flavors, as we saw in the Sankey diagram, are the top additive type ingredients. And this graph shows the distribution. We see the mean is about 16, but they can range from 1 to 54. Big variations in the use of additive type ingredients, as seen in these two categories, cookies and pastry and donuts. The average is about 15 in cookies and about 26 in pastry and donuts. Now let's move to sweeteners. The number of sweeteners used in each product ranges from 0 to 11. And about 60% of baked products report 2 or more sweeteners. Multiple sweeteners impact the listing order of sugars, of these added sugars of ingredient lists. In addition, we also found that 4 sweeteners, sucrose, dextrose, high fructose corn syrup, and corn syrup, are among the most frequently listed in sweeteners. And as you can see from this graph, this comment is not too far-fetched. Some more data that we thought may be of interest. Only 5% of the top selling baked products are wheat-free. Hydrogenated and partially hydrogenated oils continue to be used. The use of non-nutritive sweeteners is limited in baked products, with the highest reported of 4% in breads. And not all baked products are the same. For example, pastry and donuts have the highest proportion of the use of hydrogenated and partially hydrogenated oils. About 1/3 of the products reported their use. And additive type ingredients such as coloring agents are the highest in pastries and donuts. About 70% of products use a coloring agent. The past few slides that I shared with you are just a few examples of what is possible with ingredient ID. But there's a lot still needed to give the total story. For example, this is from a study in France. This is the food additive network in their foods. Some recent studies have suggested interactions of mixtures of ingredients. That is the cocktail effect of additives. And consumers are constantly exposed to this cocktail of additives. This is the same study from France, and it shows the most frequently consumed food additives by percent of consumers. The most frequent additives are modified starches, citric acid, and so on. We would like to see such studies in the US. Ingredient ID and thesaurus can make it possible for such studies to be done in a systematic manner. I hope you found some of these examples interesting. I know I find them fascinating, the possibilities. So moving on, what are we doing now and what are some of our plans in the future? Currently, we are expanding the thesaurus to other food categories and plan to do the complete BFPD. We are in the very initial stages of trying to automate the process of parsing and thesaurus building using deep learning techniques. We are trying to standardize preferred descriptors by using other established thesauruses and ontology systems. This is an ongoing and evolving process. We would like to see more food groups and ingredients characterized. For example, we just did the baked products. We would like to do beverages and mixed dishes next. We also want to do nutritive and non-nutritive sweeteners and emulsifiers because of the public health concerns. We would like to see the ingredient ID and the thesaurus used for BFPD to improve its search function and for FoodData Central to identify and prioritize commercial ingredients for inclusion. But we can do a lot more with collaborations, such as build integrated systems, for example, with food safety, environmental and agriculture data sets. Build food ontology systems where ingredient ID providing the missing piece on ingredients. There are several possibilities for data mining and research projects. And of course, what I have listed here is limited by my expertise. I would love to hear from others. The ingredient ID files can be used as training data sets to build other computer systems and artificial intelligence tools. A lot of the grunt work has been done, which I hope will help in automating other processes. This can possibly be incorporated into dietary assessment tools for us to get a better idea as to what are we eating. To conclude, some safe conclusions here. IngID makes available a framework for understanding of commercial ingredients not available before. The thesaurus can potentially improve the efficiency of data cleaning and processing of the ingredient list details and help other researchers. IngID can help characterize in foods the dimensions other than the traditional nutrient profiles and in development of food ontology, computer programs and artificial intelligence tools. Overall, it will help improve food composition databases, dietary assessment tools, study the interaction of ingredients, and precision nutrition, leading to better understanding of dietary intakes and eventually diet health disease relationships. And a big thanks to all the team members, Jane, Quinn Anne, and Shala, who have made this possible. A big shout out to Drs. Pearson and Dr. Conley for their continuous support and leadership.
Good afternoon. Today I'll be presenting the development of a nutritional knowledge database to support precision nutrition initiatives. Precision nutrition is going to require the integration of a significant amount of resources, such as big data and bioinformatics, testing services, digital applications, diet analytics, and the study of the human metabolome. Now, there is significant existing data available in online databases, particularly if we consider reactants and products in biochemical pathways or the genes involved in biochemical pathways. Also, there are databases which provide data on disease perturbations and the pathway and genes involved. And although we have significant food composition databases, there is still a significant disconnect between what's in food and what's in the human metabolome. So where we can consider incomplete data, if we take, for example, the USDA database, which is a fantastic resource and captures quantitative data on things such as vitamins and minerals in foods, simple carbohydrates or total carbohydrates, amino acids and total protein, fatty acids and total fat or total fiber. But where there's missing data is all of the other components in food which are non-nutrient in nature. Similarly, there's a significant disconnect between what's in food and what's found in the blood after we consume food. So these unknowns in foods are often referred to as nutritional dark matter. So these are molecular signals that are often characterized using metabolomics techniques. And it's estimated that we can only identify between 1 and 10% of components in foods as observed using untargeted metabolomics techniques. As I've mentioned, there are significant pre-existing databases which do capture compositional elements of foods, such as the USDA FNDDS database, FoodData Central, specific interest databases such as the polyphenols databases, NIH Office of Dietary Supplement databases. We have Phenol Explorer, PhytoHub, and FooDB. Now, if we consider what's in these databases, taking, for example, the USDA database, visually what you're looking at is a collection of data sets which have some common data elements allowing them to be linked. However, there's significant limitations for users in utilizing these databases. For one, there's limited capacity to integrate databases and data sets with each other. So there are a number of internal identifiers which allow us to link data within databases such as the USDA database, but we're often lacking common data elements which are required to link these databases to external or additional databases. So what am I talking about when I talk about common data elements? Well, within the USDA databases, we have linking identifiers which allow us to link things like ingredients to things like foods, such as the DSID, ingredient IDs, supplement IDs, FDC ID, or NDB number. However, what would be required for formal precision nutrition initiatives is if we could link these databases using common data elements to other databases, using such common data elements like IngID and SMILES, which tells us about compositional molecular structures, metabolites through linking to databases such as HMDB, also identifiers which would allow us to link to pathway databases such as KEGG and Reactome, or health databases such as CTD. So what we really need to consider is moving away from this single click in, click out interface. And by this I mean we put in a search term, we click in, we get some information, we pull the data we need, we click out, and then we go into another data set and get what we need. And what we really need to be moving towards is these networked databases. So in order to do that, we need to consider common launchpads or dashboards. So we need to be able to integrate multiple data sources for many purposes. So we may want to drill down to the source data. We may want to upload our personal data. We may want to download the results when we use these databases. We may want to link directly to other databases. And ideally, we want to be able to use some type of data visualization interface so we can visualize multidimensional data. So what are the obstacles in moving forward in this respect? Well, for one, with respect to nutrition and diet, phytochemicals are poorly represented in compositional databases. Metabolites are poorly characterized. Phytochemical taxonomy and nomenclature is poorly defined and inconsistent. And data is often scattered across multiple data sets or databases which lack these common data elements. So we started building our database using evidence mapping initiatives, which essentially is a systematic search approach, which is used to identify the current knowledge base, gaps in knowledge, or future research needs, and where the results are presented in a user-friendly format. So often a database as opposed to a publication. So our evidence mapping was designed to develop initially a static database, which allowed us to move from what we can ascertain about dietary phytochemicals in the diet to their bioavailability, their metabolites, and their analytical properties, and ultimately then linking to health effects using various existing databases. In our initial core database development, which we called Phytochemical Metabolome Database, we identified our targets using various USDA databases. We conducted a number of systematic reviews from which we extracted phytochemical composition and metabolite data. Then we moved to pulling in chemical identifiers such as IngID or PubChem ID. We had to establish our own hierarchical taxonomy. We also built a reference standard library so we could analyze these compounds in clinical biospecimens. We also modeled microbial and human phase 2 metabolites so we could build suitable spectral libraries. And then moving on from there, we were moving to develop a more graph database, allowing us to incorporate things like data visualization techniques, which I'll describe in future slides. The initial curation of the data covered over 13,000 manuscripts, and you can see here from the table on the right the number of analytes that were remaining after data set cleanup stages, where we captured anywhere from 30 analytes to over 300 analytes for a limited number of foods which were rich in dietary phytochemicals, which was the initial focus of our evidence mapping strategy. From that point, we moved from our static metabolome database to a knowledge database called the Metabolome of Food, which allowed us to move from foods to metabolites to pathways and then to disease states. We then built a team of experts in computer science and bioinformatics, including Professor Shusha Du in the Department of Bioinformatics and Genomics at UNC Charlotte, Dr. Jane Yang, Professor of Computer Science in the College of Computing and Bioinformatics at UNC Charlotte, our expert on data visualization. Alex Smirnoff from the Department of Bioinformatics and Genomics, our expert programmer and database developer. Our great PhD students, Sierra and Chao Zhang, who are involved in programming and data visualization initiatives. And then our three evidence mapping experts, Jessica, Harry, and Katie. Data coming into MetaboFood comprised compounds such as chemical name, chemical formula, monoisotopic mass, identifiers such as CAS, HMDB, PubChem, IngID, and SMILES, details on taxonomy such as phytochemical family, class, or subclass, and also foods such as food and food source. Initially, our database captured over 2,000 rows of phytochemical data from a limited number of foods. Now, the existing food and nutrition databases, which are already out there, really lay the foundation for our database expansion. So this includes extending into the USDA, FNDDS, FoodData Central, and the specific component data sets. In the future, we hope to next move on to Office of Dietary Supplement database and include some integration with Phenol Explorer, PhytoHub, and FooDB. So with respect to the USDA specific component data sets, many of you may be familiar with the flavonoids, procyanidins, and the isoflavone databases, which we've since incorporated. And also with respect to FNDDS, there are a number of updates. So we focus primarily on the 2017 to 2018, but we will update our database as these are updated by the USDA. So we need to consider, I guess, data format. If you use USDA databases, they're often data sets are captured as JSON or CSV format files. They have a number of variables and descriptors which we can use as common data elements, such as food code and ingredient code, which are linked to foods and beverages, portions and weights, and FNDDS ingredients. Also, we have FoodData Central IDs, which allow us to link to data sets such as ingredient nutritional values or FNDDS nutrient values. And these allow us to make connections between the various data sets, such as the foundation food data. So moving on from what's captured in the USDA database, next we need to embed common data elements allowing us to connect to external data sources. So these are foundational elements, and this is the process for how we capture these. So we established a semi-automated process allowing us to pull HMDB IDs, linking to KEGG IDs and Reactome IDs. And then KEGG and Reactome IDs we were able to link to pathway IDs, and then use KEGG and Reactome IDs to pull in the associated CTD disease IDs. So the goal of all of this was really developing a usable database with the focus on developing features based on intended user groups. So really we wanted to make big data publicly accessible, and that means to the lay public, not just the science savvy public, which most databases are designed for. So we wanted to include features or landing pages or data visualization strategies which would be amenable to the lay public, to people that work in nutrition, so maybe nurses and dietitians, and also researchers in metabolomics. So in building out our Metabolome of Food knowledge database, the goal is that users can visualize the uniqueness and overlap of foods using various data visualization techniques such as Sankey, SOM, and node link diagrams, which I'll show you as examples in the following slides. We also wanted people to be able to search for compounds and their metabolites associated with specific foods, and interactively explore linkages between their food, chemical compositions, pathways, and diseases. So this is just an example of different landing pages which we can create. One showing relationships using a self-organizing map, and one showing relationships between foods, their subclasses of compositional elements, pathways, and diseases. Also, we have search functions where people can search by either typing in a food or a component of a food or a pathway or a disease or a chemical identifier such as IngID or SMILES, or a database identifier such as PubChem or ChEBI. So here in this example, you can see if we type in coffee, we see the phytochemical components on the right identified in coffee, and other foods on the left, which also share that chemical compositional element. And if we were to click further on the component of 3-caffeoquinic acid, we would come to a properties tab which would list things like monoisotopic mass or IngID key or SMILES annotation. We could further click and look at taxonomical elements, such as how that phytochemical is nested within other phytochemical classes and families. And then ultimately we can click on identifiers, which will provide a list of other database identifiers which then individuals could link to. So the one element that we're using is the self-organizing map. This is just a simple representation of a small number of foods, but the foods are organized by how closely they're related in their phytochemical or metabolome compositions. And if you click on one of those foods, such as berry, it would take you to a list of the compositional elements of berry, and again, the other food sources where there's an overlap in those compositional elements. We can also use the Sankey diagram, which is a type of flow diagram which basically the flow is proportional to the abundance or the weighting of the data between two elements. So if you look here, we've got foods on the far left, and then their compositional elements on the next tab, and then we've got their pathways and the disease perturbations which they may be linked to. So we can use this diagram to explore various hypotheses in multiple different ways. So if we're interested in looking at the relationships between a food and the phytochemical overlap within those foods, that's represented here for a subset of foods, showing the uniqueness and also the similarity between compositional elements within various foods. We can also look at relationships between food, their compositional elements, and pathways, and a singular overlap, such as looking at the relationship between metabolism and a subset of foods. We can also look at more simplistic relationships between a pathway and a food, such as the immune system, and then showing the foods which have the strongest link to immune pathways. Another way we could look at this is relationship between foods and an individual phytochemical which overlaps within these foods, and how that is linked to various biochemical pathways. Or we can go more complex and look at relationships between foods, their phytochemical compositional elements, and the pathways, and how those would all link to a singular disease such as cardiovascular disease, showing the extensive overlap between multiple foods within the diet and risk factors for cardiovascular disease. There are many ways we can use data visualization. Here's another example, which is simply a bar graph showing the amount of data within the database relative to a certain disease. We can click on something such as cardiovascular disease and then click on pathways, and we develop a node link diagram showing us links between a number of selected foods and their biochemical pathways. Here, the closeness of the connection shows the closeness of the link between the food and the disease, or the connections between multiple pathways and multiple foods. And we can make this as complex as we want. In this node link diagram, it's showing connections between foods, phytochemicals, and pathways. And here it's highlighted 11 foods, 77 compositional elements that they share, linked to 213 different pathways. And there are various data analytics techniques that we can use to allow people to export the data in a visualized manner. And here's just 3 examples here, but really the possibilities are endless. And the last thing we're able to do with this database is use it to predict nutritional dark matter using AI and big data through connections between databases such as the Metabolomics Workbench and our accompanying database, ADAP, which provides big data for compound prioritization in untargeted metabolomics databases. So to conclude, metabolome of food builds on traditional food composition databases by integrating metabolite, pathway, and disease linkage data in various databases. And continued development includes expansion to other fruits, vegetables, supplements, and processed foods most common in the US diet, which will build data richness and enable connections between diet and health. And I'll end with that and take any questions if we have time.